Hello, everybody. Welcome to the test review. Now, in theory, you should have tried these problems on your own first, and then you're going to go back and compare what you did to what I did and see if what you did looks similar. Now, I'm not expecting that you will have written what I did word for word. In fact, that was super crazy detailed. But read through what I wrote and I don't know, see if that gives you any ideas and see if you've got the big parts that I talk about. Okay? So, here we go. Question 1. Construct a quadrilateral and rotate it 90 degrees around A. So I'm going to get rid of this so that you can see me do a few of the steps from start to finish. If I'm rotating around point A, then in order to do that, I need to make circles starting at A, going through the points I want to rotate. So a circle from A passing through C. And then because I want it to rotate 90 degrees, I will click on the angle tool. I'll click on C, then on A, and then on some point that's on the outside of the circle, make sure I'm going 90 degrees clockwise. There would be two places where you could get to 90 degrees, but this would be counterclockwise. So it's, this way. This way is clockwise. There it is. There's 90 degrees clockwise, and that is point C prime. Make sure that you label the points using prime notation. That's important to us. Also, to do the next point, I need a new circle. You need a new circle for every point, but the steps will be the same. You'll make a circle starting from A, passing through D, and then measure the angle from D to A, and then D prime is located 90 degrees away on the outside of D's circle. There it is. That's point D prime. I'm not going to keep doing that, but in theory, like in between, if you want to make sure you're not reusing the circles, which, don't reuse the circles. You can always hide things, and but make sure you leave the angles because we want to see that. Okay, we want to know that the angles have been rotated the right amount, or the points have been rotated the right amount. Anyway, should look something like that when you're done, except your quadrilateral might not look like my quadrilateral, but definitely a rotation by 90 degrees. Okay, question 2. This is a regular dodecagon, which is 12 sides, and I want to know the angles that you can rotate it by so that it lands on top of itself. So, short version, it's 30, and all of the multiples of 30 that work, okay? Why 30 to start with, okay? Well, if you think about rotating, okay, rotating is going around a circle, which is 360 degrees, and this shape is regular, which means all of the sides and angles are the same. So if we draw segments to each of the corners, then we're breaking it up into 12 identical pieces, and 360 divided by 12 is 30. So that gives us this first angle here that would get us to rotate like this point, for example, onto the very next point, and it would do the same thing all the way around this shape. What else? What else do I know? If 30 degrees works, then 60 degrees would also work because that would just be moving like 2 spaces around this figure as drawn right now, or 90 degrees would be moving 3 sections around. So that's what I know about this. Question 3, construct the line of reflection. Well, why not? Well, why not? To get the line of reflection, it is the perpendicular bisector between some point and its image. So for example, I make a circle from A to A prime and from A prime back to A, and then I pass a line through the middle of those two intersections, and that's the line of reflection. Feels good. I would say check out these properties that a line of reflection should have. Probably going to come up. Okay, question 4. List the sequence of translations, rotations, and reflections that will take quadrilateral nope onto quadrilateral n double prime, o double prime, p double prime, e double prime. Short version would be this sentence, okay? Bare minimum I'm looking for is the first transformation is a reflection over line G. The second transformation is a rotation around point n prime by 140 degrees clockwise. Now, how would you verify these things? Well, first off, I see this line H right here, and it doesn't matter at all. This line H is garbage. I'm going to just delete it. I know it's not important. Get out of here. The reason that I'm sure that line G is important is because I see that E and E prime are the same, well, at least they look like the same distance away, and P prime Again, they look like they're the same. It looks like it's the same figure just flipped across the line. So to verify this, I will construct the perpendicular bisector from E to E prime and from E prime back to E. Oh, lo and behold, line G passes through those two circles' intersections, meaning this is the perpendicular bisector. So G is the line of reflection. So I'm going to color those circles so I don't try and use them again, but I still want you to see them. Okay. The second transformation, again, I'm pretty sure it's around n prime because that point didn't move. That point didn't move anywhere, but all the other points did turn around the shape some amount. Okay. Definitely also not a translation because translations create a shape that is exactly the same, just in a slightly different location. It's just slid over or slid up or down, left, right. Anyway, this looks like it turned around though, around point N. To verify this, I'm going to make a circle from N prime through O prime. Oh, look, just like a rotation should, O prime and O double prime are on this same circle. And if I measure the angle O prime, N prime, O double prime, angle O no, then you find that the angle is 140 degrees. If you do this for any of the points, passing a circle through P prime and then measuring the angle from P prime, N prime, P double prime, it should be 140 degrees also. If it's not, but it's really close, then I'm sorry, but they should be about the same. Okay. Question 5, prove that vertical angles are congruent. You've seen this proof before. I think I gave it to you once. I was not as specific though that time, but again, here's the argument with greater specificity. Vertical angles, they're the ones across from each other at the intersection of two lines, like angle 1 and angle 3. Here's how I know they're congruent. 1 and 2 are a linear pair, so they add up to 180. 2 and 3 are a linear pair also. They go across this straight line, so they add up to 180. If we take those equations and we subtract, think algebra, if we subtract measure of angle 2 from both sides in the first equation and the second equation, frankly, here's what we get. Measure of angle 1 equals 180 minus measure of angle 2. Measure of angle 3 equals 180 minus measure of angle 2. Well, that's the same thing on the right-hand side. That's the same thing in both of those. So if 1 and 3 are equal to the same quantity, then the argument goes they should be equal to each other as well. That's the transitive property of equality. And if that's true, then that means that vertical angles are congruent all the time, which is nice. Next, again, you've probably seen me present an argument like this, or your teacher in class present an argument like this. But we want to show that the three angles in the triangle, 1, 2, and 3, add up to 180. This is true for all triangles. So, to start with, I'm going to make a line. You're allowed to make lines when you want to. You can make lines, you can make points, you can measure angles, you can name stuff when you want to, if that's useful for your proof. Okay, just make sure that if you're going to talk about something in your write-up, that you actually label it in your picture. Like this one talks about, I named it line P. I named this line P, so I'm going to give it a name. This is line P now. And I named the two angles formed at C. Those be these angles right here. Angle, that's going to be angle 4, and this is going to be angle 5. Notice that right now when you do the measurement tool, it just, well, obviously it gives the measure of the angle. We've been doing that, but I don't want the measure. I just want to rename it. So I'll go select the angle measurement and instead replace it with a number so that I can talk about those angles in my proof and it'll make more sense. All right, C diagram, check. Now, here's the argument. 3 and 4 and 5 together, those three angles are a straight line. They form a linear triple, so they should add up to 180 degrees, just like I want my three angles inside the triangle to do. Now, I also know that 1 and 4 are the same, and 2 and 5 are the same, because those angles are what we would call alternate interior angles. Okay, they're inside the two parallel lines and on opposite sides of this transversal, or that transversal. And we know that alternate interior angles are congruent when the lines are parallel, which means 1 equals 4 and 2 equals 5. So looking back at this first equation, if we make a replacement, two replacements, we'll substitute 4 with 1 and 5 with 2, and all of a sudden, we've got the equation that we wanted to begin with, which is 1 plus 2 plus 3 equals 180 degrees. So all three angles inside the triangle add to 180. Check. Okay, the triangle angle sum theorem, last thing. So use this diagram to prove that angle 4 is equal to the sum of 1 and 2. Okay, so to do this, again, I'll start by thinking about linear pairs. I know that angle 3 and angle 4 are a linear pair because they form this straight line, and therefore that they would add up to 180 degrees. Sometimes I see people try and do something like this. They'll be like 4 and 3 and 1, since they're all on the same straight line, they add up to 180. That doesn't work. That doesn't work. When you talk about linear pairs, it's got to be just two things that are side by side, and they have to go all the way across a straight line together. Like here's half of a circle. That's 180 degrees. Anyway, so 3 and 4 make 180. 1 and 2 and 3, the three angles inside the triangle, also add up to 180 degrees. And then very similar to what we did in the vertical angle proof, a little bit of algebra. If we take those equations that we started with and we subtract measure of angle 3 from both sides, here's what it looks like. Measure of angle 4 equals 180 minus measure of angle 3. Or measure of angle 1 plus measure of angle 2 equals 180 degrees minus measure of angle 3. It's easy to get lost in the important bits right here, but the right-hand side of both of those is the same. And so, once more, if two quantities are equal to the third same thing, okay, measure of angle 4 is equal to the same thing as measure of 1 plus measure of 2, then we conclude that measure of 4 is equal to the measure of 1 plus 2. That's the argument. Anyway, let us know if you have questions.